Thank you, Alfredo, for the introduction. I'm going to present this work on behalf of my grad student, Diego, who couldn't be here. And this is a joint work with our colleagues in Germany, Markus, Rampp, and Erwin, and Laure. And the project is framed within a research program signed between the National System of Public Universities in Costa Rica and the Max Planck Society. So as the world struggles to find new sources of energy to satisfy the high demands of the population, there are several candidate energy sources being explored, and fusion energy is one of them. It's been around for some decades, but it has received more interest recently. And it is based on the same principle that fuels the sun. Basically, you have atoms of hydrogen, and you try to fuse their nuclei, and in the process, you release energy. And if you can transform that energy into electricity, for instance, then you can have a good source of energy as an alternative to fossil fuels. So this is a picture of a device that does that. It's an experimental device. It was built in Costa Rica by a group of physicists at the Plasma Laboratory in one of the universities. It's called a sterolator, and this device, what it does is using coils to magnetically confine a gas in a plasma, and then use fusion, nuclear fusion, to transform the heat into electricity. So the design of this device is tightly coupled to the simulation, which is what we have been doing lately with that group. So basically, we built with them all the simulation framework and scientific visualization to mainly get two main objectives. One goal is to design the new coil structure of future plasma fusion devices, and the other is to understand many physical properties of the plasma confined. And one of those properties is what you see here on the right side, which is the volume of the plasma being confined within the device, and also other different physical properties. For instance, when you do some intersection of that plasma with different planes. In the method that we're using, it's called BSMR, and the program is called BS Ultra. It's an acronym of the numerical method that we're using. So this program, it's a field line tracer. It works by simulating the trajectories of different particles, and it has a Runge-Kutta method of fourth order. So basically, you have a particle, and you need to understand how that particle interacts with all the different magnetic fields of the coils. So you go coil by coil in each segment in the coil. So basically, we have a 360 degrees for that segment, for each segment. And you compute all the interaction between the coils and the particles. What you're trying to understand is the trajectories of all the particles, and that will define the plasma volume. So at this point, we have not injected particle interaction in the code, so you will see it's roughly a simple code to parallelize, but it's complex enough to let us understand a few things about the architecture, the computer architecture that we are using. So the code, as I mentioned, it doesn't have particle interaction yet, so there is very little synchronization between the cores. It initially was developed for the Xeon Phi KNL processor that we have at our lab, and but some other people still have this Intel processors. So it uses MPI plus OpenMP plus vectorization in different kinds to accelerate the code. And just to give you a sense on how the code scaled, here are some results on Vega supercomputer at our Argonne National Lab, where we were using up to 1,000 nodes. That is 64,000 cores, and the code strongly scales and also weakly scales. And in this scenario, we were using 1 million particles for the simulation. So VS Ultra then scales pretty well. What about GPUs? As GPUs get more and more traction every day, since we have the convergence of HPC and data science, and now artificial intelligence. So how can we incorporate this into VS Ultra? So I'm just showing a picture here of the latest, the top 500 list. And this is a picture showing the share of the systems that use GPUs. So you can see it's roughly 30% of the list using either NVIDIA or AMD GPUs. But it actually represents roughly 60% of the performance share, right? So 30% of the systems represents 60% of the performance. So it's clear that GPU can definitely provide a lot of parallelism. And the question that the research question that we started with in this project was, can OpenMP Offload be productive to get the performance portability for the program that we have, VS Ultra? And OpenMP was chosen because we already had OpenMP-based code. And we were also thinking if it was possible to avoid platform-specific optimizations for that code. So just to give you a spoiler here, the answer that we got to these questions was yes and no. Okay, so a very quick overview of GPU OpenMP Offload. So basically, you need to, like any other OpenMP code, you insert pragmas into your code, but you gotta be careful about mainly two things. One is memory management and all the required changes in your data structures, and the other is the execution. And here, I'm using a more general term, which is heterogeneous execution, how you divide the work, for instance, between CPU and GPU. But I will concentrate mainly on what we did, which was just the offload part, okay? So we didn't do a heterogeneous execution. Instead, we concentrated on offloading the code. Right, so in memory management, we used to have this nice structure in the code with structures for particles and all the different coils and all other elements in the simulation. And that worked pretty well in the original version, but it doesn't really fit the structure that you need for offloading code onto the GPU. So we had to transform that into simpler one-dimensional arrays just to make sure that the data transfer was efficient enough. And that's a first concern that we had to tackle in order to port the code to the GPU. All right. So the other thing is what exactly you want to offload. And here we experimented with different pieces of the code until we realized that the main, or the most promising piece of the code was each iteration of the loop of the method. So basically, the compute iteration was going to be uploaded onto the GPU, and the grain was a bunch of particles. So basically, we didn't get parallelism inside, say, the coil computation, but it was better at the level of each particle. Okay, so I'll show you later how we inserted the pragmas for the parallelizing the computation. But here I'm just showing you a simplified version of the pragmas for data transfer. So basically we wrapped the computation-based part of the simulation with these two pragmas, the enter data, where we send basically all the information from coils, particles, and a few more things, and then the exit data. And in the middle, since we need to create the trajectories, we are checkpointing, so to speak, or getting an image of the particles every 100 iterations. So that was roughly all what we needed after we understood what piece of the code was to be parallelized. Now, regarding execution, as I mentioned, we divided the particles into the different cores, and for that we used two approaches. One is a prescriptive approach, and here you see just a summary of the pragma. So basically, we divide the number of particles in each iteration onto the different cores of the GPU using just this pragma. Because this is a prescriptive version, you have to specify several different parameters of the pragma. But basically, this was the general structure of the code. And we also compared that to a descriptive version in which you don't specify that many parameters, you just let the compiler do the job. And we were also interested in that version and see how both the prescriptive and the descriptive version compare to each other. All right, so for the setup, in the experiments we use 3 systems. We use the Raven supercomputer at the Max Planck Institute. It's got a few nodes, but some of them have NVIDIA A100s, which were the NVIDIA architecture that we tested. We also use a test system with AMD MI250. And here each node has 4 of those GPUs, but each of them has it's a multi-chip module, so we only use one module. So you will see that the experiments, the performance in the experiments only represent half the power of the GPUs. And we also use a test system by Intel, which is a preview hardware of the upcoming Intel Xe GPU. Unfortunately, we were not able to publish these results, so I cannot comment on those results, but clearly those were not promising results performance-wise, so we were not able to put them in the paper. So what we can report is our approach works on the 3 platforms, NVIDIA, AMD, and Intel. So here are some configuration for the different platforms. Here's the Intel compiler that we use for the CPU version, and all the configuration for NVIDIA, AMD, and the Intel's GPU version. And just to move quickly through the results, here's a baseline comparison between the CPU that you see here, the NVIDIA, both the prescriptive and the descriptive version. So remember, prescriptive is when you as a programmer give all the details. Descriptive is when you let the compiler figure out the best combination of those parameters. And here's the AMD results. So we used 3 different problem size. This is roughly 100,000 particles, 500,000, and 1 million particles. And first of all, well, GPUs are great comparing to the CPU counterpart. And I want to mention this CPU has 72 cores. It is already using OpenMP on all the cores, and that code was, optimized in the original version. So we compared that version, the best CPU version that we had, and you can see the best speed up that we got after these are average results. results on 10 repetitions was around 6x acceleration with respect to the original CPU code. However, if you analyze the peak performance of this GPU by AMD, we still are far from exploiting all the power of that GPU. So it really needs more study on what are the performance bottlenecks. And one possibility is the compiler that we were using, the client compiler, is not as mature as the tools that you get from NVIDIA. Also, when we compare the prescriptive and the descriptive version, they're really similar between them, but still using some NVIDIA tools like Inside Compute, we were able to see that we are still there's still room for optimization, and it's a future work in our study. All right, so I'd like to also mention that we run a scaling test from 1 GPU all the way to 32 GPUs, and both strong and weak scale. The system does pretty well. Here are some problem sizes that we were using. And I want to wrap this up by saying that this work was possible by the research program between Costa Rica National Council of Rectors and the Max Planck Society. We got help from NVIDIA, AMD, and Intel for the different experiments. So I want to thank all the guys that supported us. And also I want to acknowledge the RISC-2 support for coming to this conference and present this work. I want to leave you with some final remarks. So we ported this field line tracing application on GPU. We got performance portability, but still there is missing the last performance optimizations that presumably has to be they have to be specific for each architecture. But we believe that as compilers become more compliant with the specification, it will be possible to reach a better scenario in which you have performance portability. We definitely need to go deeper into both the AMD and NVIDIA platforms to understand some of the still present performance bottlenecks. Okay, thank you so much.
Thank you.